Alright, so in this video we're going to discuss equipotential surfaces. And equipotential surfaces are three-dimensional surfaces on which the electric potential is the same at every point. So I have some images here of some equipotential surfaces. Now keep in mind, once again, we're limited to 2D. So technically these circles, green circles here, which are equipotential surfaces, should be green spheres, hollow spheres, rather than the circles I have drawn here. But it's very hard to show anything that's three-dimensional. And you can see as you change the distribution of charge, what your equipotential surfaces are going to look like are then going to depend upon that distribution of charge. So these are points where the potential is exactly the same value. So you see it labeled here 8.2 volts. And it makes sense that these are circular because for a point charge, the potential goes as 1 over r. So you're just going to see at each radial distance away from the point charge, the potential is going to be the same. And you'll notice, no matter what the distribution looks like, the electric field is perpendicular to the surface. So it's perpendicular to the circle for the point charge, and then for this line of charge I've created, you'll notice here that the equipotential surfaces go like this, but the field lines go this way. So the electric field point's always perpendicular to the equipotential surface. And you'll also note here that none of the equipotential surfaces actually cross each other. So no matter how weird they kind of look based upon how you change the distribution of charge, they're never going to cross over top of each other because no 2 points can have 2 different potentials. I do want to make a couple of special notes for conductors. If the charges are in rest on the surface of the conductor, then the surface of the conductor acts as an equipotential surface, and the solid volume of the conductor will have the same potential. And we know this because the potential difference has to be 0. Remember, the potential between 2 points, or a potential difference, is equal to integral of the electric field in terms of the path length. Since the electric field inside of a conductor is 0, that means that the potential difference inside the conductor has to be 0. So it has to be the same value so that when you subtract the two numbers, you get 0.